gram-positive and gram-negative graphic. Don't forget, when we talk about the gram stain, what each step is and what it does. We talked about it when we went through this graphic in chapter 4. So the primary stain is crystal violet, so that it percolates down into the structure. The iodine works as a mordant, so what that does is it cross-links the crystal violet into the structure, so it's not so easily washed away. The decolorizer, we're using acetone right now. You can use 95% ethanol. What that does is it rinses away that outer membrane and takes all of the color out of the gram negatives. Doesn't change the gram positives.
It rinses away what?
Say again?
What does it rinse away?
It rinses away the outer membrane and it leaches all of the color out of the peptidoglycan.
And that's the one that's
In
very
the gram
time-sensitive.
negative. That's the one you have to be really careful and time very carefully. And that's why you need the counter stain, because the alcohol takes all the color out of the gram negatives. You can't see clear cells. So that's why you use the safranin. So the safranin colors the gram negatives pink, and then the gram positives stay purple. Okay. So we'll look at the questions in the gram stain in just a second. So you guys did the simple stain. So we used crystal violet, we used methylene blue, we used safranin, and all of those were cationic dyes. Remember?
Yes.
Cationic dyes are positively charged dyes. So those adhere very tightly to the surface of the cell. Sometimes we call it positive staining because they're positively charged dyes.
Crystal violet, methylene blue.
And safranin.
And safranin.
All of those are cationic dyes.
You will ask us about the seconds we're going to stay on there? Like the 30, 60?
No.
Okay. Thanks.
So you guys did the negative stain and the capsular stain, and you remember we used acidic dyes when we did those two. So those are negatively charged dyes. So they don't adhere to the surface of the cell, they stain the background. So when we did the negative stain, we used nigrosin. When we did the capsular stain, we used Congo red. So both of those are negatively charged dyes. So they adhere to the background.
And the crystal violet and all those are cationic negative,
No,
positive ion.
they're positive. Yeah. Cationic's positively charged. Right. And you remember the negative stain and the capsular stain are the exception to heat
Heat
fixing.
fixing, you don't.
So we don't heat fix those.
What's this?
You don't
The
heat
negative and
fix
the capsular, you do not heat fix those. Everything else we do, we heat fix.
Will you ask about the molecular motion of the nigrosin? Okay.
That's not it. This
You
is-
about to find me.
I'm just trying to make sure it's not a trick question. Might be a bonus ID, those 12 points.
Which one did we heat fix only?
We heat fix everything except the negative stain and the capsular stain.
Do you remember
Negative.
Ms. Nicola told us, she said, y'all should
Now, when we did the simple stain, what was the information we got from the simple stain?
The simple stain was the first one. I thought the first. Wait a minute, I'll tell you.
What information do we get from a simple stain?
Oh, no. Let's go over here.
You get 3 pieces of information.
Oh, isn't that like the shade?
Mm-hmm.
We get the, you're right. We get the shape, the.
Size?
Size.
Oh,
Mhm.
look at me. If I can-
All of them physical though.
if I
You
can-
get the size, shape, and arrangement.
Arrangement. That's
Okay, I was
the third
thinking
one.
Size, shape, and arrangement.
Okay, I was.
So that's all
You
you
should say
get
it.
from a simple stain. We don't do a lot of
just messing.
simple stains unless that's all we need to know. Because we can get that same information when we do a gram stain. Okay, so we usually don't do an awful lot of simple stains unless we only need the cell shape, size, and
The
arrangement.
physical.
So let me go, while we're on subject, why do we heat fix? This is in that simple
To
stain.
kill the.
To keep it from
Kills
washing,
it.
to keep it from washing away when you
This
stain it.
makes it adhere to the
Adhere to
surface, so it
surface,
doesn't
yeah.
rinse away.
Yeah.
And lastly, kills it, makes it adhere to the surface, and coagulates the proteins. That
Yeah.
thickens it up, makes it more visible. So those are the three reasons why we heat fix.
So,
You
coagulate,
expect that question.
wait.
To surface.
Adhere, kills, and coagulates.
Coagulates the proteins, that thickens it up and makes it a little bit more visible.
Visible.
Okay, so now let's go back and look at those questions in the ground stain. So these are, in my book, it's 194. We didn't do this already, did we? I didn't think so. So ground stain at the end, there's one page of questions. The first question gives you a lot of mistakes. So what happens if? So I think the first one is, what happens if you don't use the iodine?
You
So
won't
what
have
needs
it
to
cross.
jump in your mind when you see
cross-linked.
that is, what does the iodine do?
Cross-links to the
cross-links.
crystal violet.
It
What made it
cross-links the crystal violet. So how
Oh.
would that affect your end
190.
result?
It would wash out.
Yeah, all the color would wash
No,
out.
194.
And then when you counterstained it at the end with safranin, everything would be pink. Okay?
Okay, can you repeat that again, please?
If you do not use the iodine, there's no cross-linking.
Okay.
Therefore, the alcohol would wash all the color out. And at the end of the procedure, when you counterstained it, the end result would be everything would be pink.
So iodine cross-links.
Iodine cross-links the crystal violet, so it locks it in position, not so easily rinsed away.
It's a mordant.
So iodine functions as a mordant.
So we take this test.
I like that word.
A week from tonight.
Okay, I'm gonna say it again. So the iodine cross-links, alcohol washes all color out, so it's pretty much liquid pink.
When you counterstain it, everything's pink.
Okay.
So specifically, the iodine cross-links crystal violet. Okay, then the next question asks you, what if you forget to decolorize?
We will not take a lot of ground negative stuff.
Okay, so you don't decolorize, you're not gonna take the crystal violet out of the gram negative, so what's everything gonna look like at the end?
Purple.
Everything's gonna be purple. So again, you're not gonna get a differential result. Make sense?
Mm-hmm.
The next question is, what if you forget to counterstain it? So what if you forget to use the safranin?
Then you won't be able to see the gram. Wait, I'm gonna tell you. You won't be able to see the gram. You won't be able to see the gram negative stain.
Correct.
Because they're clear unless you
Exactly.
use the
Exactly.
I don't. Yeah.
So if you don't use the safranin, your gram negatives are not gonna be visible. You'll still see the gram positives in there if they're present,
Purple.
but you won't see the gram negatives.
So I have a question. So if we forgot to use the iodine, would something that is actually gram positive, would that actually end up indicating, it would look like it was gram negative?
Exactly. It would look gram negative.
Oh.
And the last
That's a
one
good
says, what if you reverse the crystal violet and the safranin? So what if you use the safranin first and the crystal violet last?
You still gonna end up wiping away the gram negative.
It'll look
Because
purple.
iodine doesn't cross-link safranin.
Oh, that's right.
Iodine doesn't cross-link safranin, that's one problem, so probably all the safranin is gonna wash out.
You won't be able to.
But what's gonna happen if you use crystal violet last?
Everything's gonna be purple.
Everything's gonna be
You
purple.
want to differentiate it.
So again, you're not gonna get a differential result.
like that.
Very good, you guys got it.
Wink, wink.
Number two is a really good question. You know, both crystal violet and safranin are basic stains. We already talked about that. We used them in simple stain. They very tightly adhere to the surface of all cells, right? So why do we get a differential result in the gram stain?
Because
If crystal violet and saccharin are both cationic stains, they both work the same way, they both stick to the surface of the cell, why is it that we get a differential result when we do the gram stain?
one is gram negative and another is gram positive.
Well, that's true, that's a true statement.
It doesn't got something to do with the cross.
But what does the negative and positive come from?
The cell walls.
The cell walls, okay? And what makes the gram stain work the way that it works?
The heat. The heat.
No, we didn't
I'm
heat
just
that
guessing
one.
heat. No, we didn't heat that one.
But you're on the right track.
Oh, like when you was telling us about the cell walls being open and receptive
Well, that's in the
inside.
endospore stain.
I don't know. I don't know.
Speaking of those.
What do you think?
You said what makes it differential between the two?
Let me ask you this. Do we do the simple stain and the gram stain exactly the same way?
No.
No, not at all. So in the gram stain, you have those very specific steps that you follow. And you use the iodine, and you use the alcohol, and you use them in order, right? So that's why you get a differential result. Even though they're exactly the same stains, they're both cationic stains, they give you a differential result in the gram stain because of the steps that you follow in the gram stain. If you don't do it right, you won't get a differential result.
So the steps that we follow will give us a differential result.
Exactly. It's the steps in the gram stain, the use of the iodine and the use of the alcohol in the order that you use them. That's what gives you a differential result.
Oh, that's the one we use we did the dye on the end. Okay.
You guys saw large eukaryotic cells in the preparation you made from your gum line. They were most likely your own epithelial cells. They were actually squamous epithelial cells. The question asks you, are you gram positive or gram negative? What do you think?
Gram negative.
Think so?
Yeah, because the bacteria is purple.
Nothing. Well, we're not talking about the bacterial cells. We're talking about the squamous epithelial cells.
Gram positive. I don't know.
Think so?
I say negative. That's just because I don't know, babe.
What does the gram stain work with? Dre, you said it earlier.
The cell wall.
The cell wall structure. Do we have a cell wall structure?
Yes.
No. Squamous epithelial cells are animal cells. They don't have a cell wall. So we're not prokaryotes.
Plants. Yeah, we're not plants.
We're eukaryotes.
Yeah.
So you get a differential result with eukaryotes. You get a consistent, predictable result with prokaryotes because it works with the prokaryotic cell wall. So usually we see some pink and some purple squamous epithelial cells. There's nothing that governs that process. It's just as likely to take up one as it is the other because they're eukaryotic cells. They're not prokaryotic. Does that make sense? We're neither.
Neither.
We don't have a prokaryotic cell wall. We are neither. We are not prokaryotes. The gram stain works with prokaryotes, not eukaryotes.
Oh, man.
I think we actually talked about that last one. One of your lab partners has done the gram stain over and over and over and keeps getting a pink result. So what do you think she's doing wrong? She's not getting a purple. Something that's supposed to be purple is
She's
still
not
coming out
leaving
pink.
she's not leaving.
She didn't use iodine?
Or she's not using the,
That's
That's
possible.
possible.
She might not be using the iodine, may not be using the iodine long enough.
yeah.
Or
I thought,
she could be,
Keeping the acetone on for too
yeah,
long.
over-coloring
Over-coloring,
it. So she could
yeah.
be keeping the acetone on there too long. Remember I told you to hold it at an angle and just let it drip over the surface? So you gotta time that step very carefully. So any questions about any of those?
I do have a question. What is the A? The A is Or gram stain, what was that acronym? You got CD, I know what those are, but.
Alcohol,
Alcohol.
we're using acetone right now.
Okay.
It can be 95% ethanol, which is alcohol,
Okay.
or acetone. Either one will work. So we've got acetone right now.
I have a question. What was the explanation again if we don't, if we didn't decolorize? I know that everything would eventually end up being purple, but what was the,
If you did not decolorize.
if we did not decolorize?
You wouldn't
Take the
take
color out the red,
the
so-
crystal violet out of the gram negatives, so everything would
Everything
stay
would stay
purple. Everything would stay purple. Right.
And these questions will probably be on the test.
But some of them will.
Mhm.
No.
So y'all did negative stain, capsular stain, grass stain, you guys did the endoscore stain.
That's the one we
Remember-
do the boiling over water thing.
Yeah, we talked about the fact that when you do the endoscore stain, you always stain an older culture. It wouldn't make any sense to gram stain a 24-hour culture because it's still got plenty of food and water.
Right.
And
So
then-
it only sporulates when the environment's drying up or it's running out of food. So we always endospore stain older cultures.
Because it's dehydrating and running out of food.
Yeah, it's gotta be running out of food or the environment's gotta be drying up, that's when it sporulates.
I think you said that.
You remember, that's the one we put on the beaker and we steamed it. So what happens when you steam it is you open up that keratin structure and that lets the malachite green inside. And when you take it off the heat, the keratin shrinks back down and locks it in. It traps the malachite green in that endospore. And then when you take it to your sink, malachite green is a water-soluble stain. So that malachite green is rinsed out of everything but the endospore. And then you counterstain it with safranin. And all you guys got really good results with that one. You remember we had green spheres, and then we had larger pink cells, and those were the vegetative cells. Those were the ones that were still growing and dividing. Okay. I think your lab book asked you about a control. We don't need a control with an endospore stain. They're either there or they're not. If you're working with an old culture, they're either gonna be there or they're not. So you don't have to have a control. Now, you guys remember, and this is one of the questions that's in the lab book, remember when we did the simple stain, right? The Bacillus cereus, you could see those endospores in there, remember? They were clear, they weren't colorized, they were like little vesicles inside the rods. Right, everybody remember seeing that? Well, if you can see it without doing an endospore stain, why do we do an endospore stain? What do you think? We saw them when we did a simple stain. But then we turned around and did an endospore and colorized them. Why do you think we need to go through the process of doing an endospore stain?
To see if it's. Wait a minute. Can you say that one more time?
Why did we go through the process of doing an endospore stain if you can see the endospores without doing an endospore stain?
Does the endospore stain reveal more information than just the size, shape, and arrangement?
It showed that there's like the four together. When we
And
did
that's the tetrax. That was the negative stain. I don't think the tetrax.
So you asking what would be the purpose of us doing
Yes,
that?
it is.
To be
Did
able
we
to,
talk about
to see if
Uh-huh.
I was gonna say to see if they're only visible when the conditions are harsh, and you said we could see them.
Early fall, yeah.
So we will be staining them to see. I want to say, I guess, to see if they're active or if it's,
Well, they're not active.
or not active, but if it's.
I think you kind of
I
on the
can't
right
say it.
track.
I know what I'm thinking, but I can't say it.
Did we talk about anything else that might be inside of a cell? Chapter 4.
Oh.
Did we talk about anything else?
Wait.
What did we talk about?
No.
Did we talk about some storage vegetables?
No.
We talked about
No.
inclusion bodies.
Oh,
as
yeah.
well.
That's
So
it.
that could be an inclusion body.
Okay.
If it's a clear sphere, we don't know for sure what it is. So doing the endospore stain confirms
That is, okay.
it's an endospore and it's not
Something else. Okay. That's it.
That's it.
That's it.
That's
So let me write that down.
Those clear spheres could be a lot of different things.
So endospore stains.
But only the endospores turn green when you do the endospore stain.
Rule out inclusion bodies.
Yeah, and
Okay.
it verifies that that is indeed an endospore.
Okay.
Oh, malachite green?
Malachite green is the primary stain, saffronin is the counter stain.
What is it doing now?
It
Inclusion
rules
body.
out that it's an inclusion body or something other than an endospore.
It turns green if it's an endospore?
Yes, remember we saw the little green seed?
Like you told us before about staining, you said sometimes if it gets contaminated or cross-contaminated with something else, you be able to know when you do the stain.
Oh, yeah, you'll see
Everything
it.
will stick out.
You'll see
Yeah.
different cells if there's something in there that's
Not
not
supposed to be there.
I have a question.
Yeah.
With the thing when you said, well, we do not need control with endospore stain,
Mhm.
why?
because they're either there or they're not.
That's why.
So
you
we
use the old
always
one.
start out with an old culture.
What page is
So if it's an endospore former, it will have made endospores by that
And
time.
it'll be revealed by the green.
And they would be revealed by seeing the green.
Okay.
Exactly. So we don't have a control for that one.
Cool beans.
So any other questions so far?
So I see then why we wouldn't need a control for the endospore stain, but then why would we need a control for any of the others?
Well, like for the gram stain, if you have a known gram positive, you can use that as a control against your stain that you did to see if it is gram positive or gram negative. So if you can use those for comparisons. With the endospores, they're either there or they're not there.
So it said, what does a positive result for an endospore stain indicate about the organism?
So what does that tell us if we see the green spheres?
It's an endospore.
It's an endospore
Okay.
former, so it's gonna form those endospores and it's gonna persist in the environment.
Okay.
If they're absent and it's not an endospore former, that's gonna be a much more easy organism to kill because it
Okay.
doesn't have those endospores. Remember, endospores, the only way we can destroy them is by autoclaving them. Chemical treatments, disinfectants, they don't do anything to endospores. So, any other questions?
When you said about the patterns and the arrangements, you were meaning
Yeah, diplococci,
Okay.
streptococci, tetraad,
No matter what.
sarcino,
Okay.
spirilla, all the shapes and
it?
arrangements. So they're in the lab book, but they're also in the lecture material. for
Yeah,
chapter
on
4.
the expert, on
And
that.
that's where I got that handout that I gave y'all earlier in the semester, was actually chapter 4.
Is this one?
That one right there that's on the list.
Yeah, that
Oh,
one.
So, we do negative and capsules things the same?
Basically,
Same
yeah,
process?
it's just, it's a different stain, but you follow the exact same process. Yeah, you don't heat fix it,
So
you
you
put it
mix
on
it
one
with-
end, and you slide it
Okay,
across to
okay.
create a real thin
Except
film.
for this. Well, no, it's on here too.
But did you mention, I had wrote down somewhere, paleomorphic?
Pleomorphic.
Pleomorphic.
Pleomorphic means they take on a lot of different shapes.
Okay.
There's actually an example there on your,
175.
on your handout of pleomorphism.
Okay.
I think there was one on there.
Mm.
I didn't see it.
No, it's on
Maybe
the,
not.
I think it's on 175. That's what
Maybe
it
it's in the
is.
lab book, yeah.
Like,
Pleomorphic just means they take on a lot of different
I didn't see
shapes.
them.
they're just bunched together all kinds of ways.
Yeah, they can actually appear as cocci, they can appear as rods, they can appear as filaments.
You said it's on
So there are a lot of different
175.
I
shapes.
didn't see it.
It's right there.
Oh, that's it.
Can you walk us through the format of the next lab exam?
It's gonna be very similar to the ones you've taken before. There's gonna be a practical part, and then there'll be a written part. So we'll probably do the written part first, and then as people finish, I'll let them go ahead and get started on the practical part.
Will
So
it
you'll
all
do
be
that
here?
as an individual. Yeah.
You mean practical as in hands-on?
And hands-on,
Oh.
you'll be doing stain, you'll be finding it on the microscope, you'll be answering some questions.
Oh, okay.
And I'll have to see it on the microscope before you
Okay.
take it off.
Oh, Lord.
So what did we put at the end of the slide?
Handicapped and all.
What, we put
On
our
the
stain,
negative encapsulate
we
slide?
put our
Right.
stain,
Yeah,
so we
okay,
use the
okay.
Congo
Stain.
red or either the
Right.
dinoxin.
It's just-
And you
I'm
actually
messing up
stir the
my
specimen
thing.
directly into the stain.
And then.
Oh, yeah,
And
microscope.
then you see it.
It might be that microscope too, though. It could be, if you put it on another one, you can see it. It probably might be.
The last one we did Tuesday, that was our
All right.
Graham.
I was making sure I
We did
had.
ground stain.
I wanted to ask one more question about
Yes,
that.
ma'am.
Simple stains. Did we go over the questions on
We haven't done that stuff yet.
there? Oh, okay.
Yeah, we did all the shapes, yeah, and sizes, shapes and arrangements, but we
Yeah.
haven't done that backstage yet.
Okay.
So y'all wanna do that now?
What?
Yes.
Okay, they ask you those questions and give you those formulas, but I've never felt like the lab book gave you enough information to answer those questions. So when you're looking at bacterial cells, the easiest thing to do is to treat them like they are a geometric form. So we treat a coccus as though it were a sphere, and we use the same formula to determine the surface area and volume. The easiest thing to do is treat a bacillus as though it was a rectangle. So you, let me just put the formulas up here. So for the sphere, for surface area, the formula, let me get it. For surface area is 4 pi r squared.
Wait a minute, is that even blue?
And this is your r, that's your radius. And pi, of course, is 3.14.
Are we being tested on this? So we need another
What?
formula?
I'm gonna give you the formula. I gotta plug the numbers in, I wanna get the right answer.
Okay.
So, pi, if you're using an old calculator, you may have to put that in, 3.14.
I'm watching.
If you're using a newer calculator, you can just use the pi function. So I'm gonna give you some examples. Now mine might be a little different from what you might get with your calculator, depending on whether you're using the pi function or actually plugging in 3.14. So let's say that the radius of this cell is 1. So we're not gonna worry too much about 1 what. We're just gonna call them units, okay? So if the radius is 1, you just plug that in to your formula. So it'd be 1 squared, which is still 1. So you just multiply the cost, and that would give you 12.56. And that would be units squared, because your formula, your radius is squared. So that's always units squared when you're talking about surface area. For volume, it's 4/3 pi r cubed. So again, you're just plugging your value in. That's really the only variable. So you have 4/3 pi 1 cubed. So if you multiply that out, you get 4.19, and that would be units cubed, because your radius is cubed. So you always have to determine the surface area, you always have to determine the volume. Then you determine the surface area to volume ratio. Have y'all done ratios in other classes? Okay, how do you do a ratio? So if I want a ratio right here, my surface area is 12.56, and my volume is 4.19. So how would I get a ratio between those two?
Usually we would have had some initial, I don't know, something would have been like a problem to kind of ask us to give the ratio based on some information. This kind of just like there.
What did you say, Giselle? You said the
A
units.
ratio. So whenever, you're right, you got some data, you got a starting point, and you're looking for the ratio between the two. Whenever you're taking a ratio, you divide both sides by the smaller number. So you're gonna divide both of these by 4.19. So that gives you a ratio of 3 to 1. 12.56 divided by 4.19 is about 3. So that gives you a ratio, surface area to volume, 3 to 1. Having a large surface area to volume is a good thing for a cell. You think about it this way, the volume of the cell, all the stuff inside, is dependent on that surface area to deliver all the food, all the nutrients, all the water, all the oxygen. Everything has to come across that membrane. So the volume of the cell is dependent on that surface area to get everything that it needs. So usually having a very large surface area to volume is a good thing. The smaller something is, the bigger the surface to volume ratio. You guys, a lot of you already had A and P, right? Y'all remember talking about the alveoli in the lungs? The reason they are small, the reason you got millions upon millions of those little bitty alveoli, remember that's where gaseous exchange occurs, is because the surface area to volume ratio is much larger the smaller it is. So you got lots and lots of area for gaseous exchange. What happens in a disease like emphysema? All the little alveoli start to fuse together. So rather than millions of teeny tiny little sacs, you got great big huge sacs. And you reach a point where the surface area can't provide enough for the volume to stay alive. In our case with the alveoli, the surface area of the alveoli can't get enough oxygen across the membrane to deliver to the cells, and the person literally suffocates. So the smaller something is, the greater the surface area to volume ratio. And that's a good thing as long as the cell is in a good environment. Now, if you take that same cell and put it in a poor environment where it's dry and the cell's going to get desiccated, it's going to start to lose moisture and nutrients to the environment, having that large surface area to volume becomes a detriment when you move it into a bad area. As long as it's in a good area, having a large surface area to volume is a good thing. Okay? So let's look at what happens to our surface area to volume ratio as the cell gets bigger. So let's say it goes to a radius of 2. So let's say it doubles. So just plug that into your formula, 4 pi 2 squared. So that gives you, I believe, 50.4 or 50.24. And again, that's units squared. Just plug that same value into your formula for volume. I believe that's 33.52. That's units cubed. So surface area is 50.24, volume is 33.52. So you divide both sides by the smaller number, and that gives you about 1.5 to 1. So surface area has gone down significantly. It's actually by half when it doubles in size. Makes sense? And now it's becoming at a disadvantage depending on how much it actually needs and what it's capable of absorbing.
And if it was, and if both of these were put into a more, I don't know, a bad area, a bad area, the larger one would perform worse?
Yes,
quicker?
exactly. It would dry out quicker, lose moisture and nutrients to the environment. So let's look at what happens with a radius of 3. So you're just gonna plug it into your formula. So that's about 113 units squared. 4 thirds, 3, whoops. I put 2 there, that should be 3. And that would be 113. Yes, cubed. So, do I even need to divide that one out? That's 1 to 1. So let's say this cell, let's call this one cell A, and let's say this is cell B, and let's say this is cell C. So let's say cell C is capable, so cell C, well, let's just start out with what it needs. Let's say cell C needs 2 units of food per unit cube of volume. And let's say it can absorb 1 unit of food per unit squared of surface area. So, how much does it need? It's 2 per unit cubed of volume. What are my units cubed of volume? 113, right? 2 times 113 is 226. So it needs 226 units. How much is it capable of absorbing? Only 1 unit, right?
Yes, it's 130.
Per unit squared of volume. These are my unit squared of volume, right? Everybody agree with that? So 113 equals 113. So is that cell in trouble? It's bad.
It is.
It's real bad. It needs 226, it's only capable of absorbing 113. So there's no way that cell's gonna survive. Does that make sense? So that's what you have to take into consideration. You gotta first figure out the surface area, you gotta figure out the volume. I may ask you to determine the surface area to volume ratio, so you need to know how to do that. And then I may give you some data like this. I might tell you, well, your cell needs a certain amount per unit cubed of volume. It's only capable of absorbing a certain amount per unit squared of surface area. And then I would want to see what you come up with, and you tell me if that cell could survive or not under those circumstances. Make sense?
Mm-hmm.
The math is really very simple. I would encourage you to do it exactly the same way every time. That way you don't get these switch backwards and you keep everything in order. That way you're not going to get lost in a problem. As I said, I'll give you the formulas. So I copied my notes for you just so you'd have a few more of these.
Thank you. Thank you, thank you.
So let me go ahead and get those out.
I forgot to wear it something.
I'm just, that's what I'm just saying. If you didn't come today, you missed a whole heap. Not a lot, a heap. Yeah. You're in trouble. Like that sale right there.
Hey,
So if you look at the top there, and those are the ones that I just did, so I
Yeah.
worked out each one of those ratios for you. The smaller the cell, the greater the surface area to volume, so we talked about that. As the radius increases, the volume increases much faster. The reason is because the volume formula goes up by the cube. So volume is always going to increase a lot quicker than surface area is. And that's what I've shown you with the little arrows here. So if you go from 12.56 to 50.24, you've gone up by a factor of 4. But if you look at the volume, same level, that goes up by a factor of 8. If you look at what happens between a radius of 1 and a radius of 3, when you go from 12.56 to 113, that goes up by a factor of 9. And then the volume goes up by 27 times. So, you understand? So volume increases a lot faster than surface area does. And I've given you a few more problems. So cell A needs 5 units of food per unit of volume in order to survive. So cell A, remember, had a volume of 4.19. So that's 5 times 4.19, or 22.6. It can only absorb 2 units of food per unit of surface area. So the surface area is 12.56. So 2 times 12.56 is 25. So would that cell survive? It needs 22, roughly 23, and it can absorb 25.
Oh, that's good.
Yeah.
So,
It can absorb more than it actually needs. Does that make sense?
Yes.
So everybody can do that. I gave you one other one on the back. I'll let y'all look at that one. Oh, this is not in the lab book. It doesn't tell you this, but it's an excellent time to mention it. As the cell gets bigger, okay, volume's going up, the cell's reaching the limit at which it can support itself, that's when it divides. So that's what triggers binary fission, because cells want to stay small. So they'll increase, and then they'll divide into 2 cells, so they start over smaller. So that's one of the things that triggers binary fission. It keeps cell division going. Make sense? And down at the bottom, I already said this, typically a large surface area to volume ratio is a good thing as long as the cell's in a good environment. That's going to favor the uptake of water and the uptake of nutrients. You take that same cell and place it in a bad environment, that large surface area to volume becomes a detriment for the cell, because now it's going to lose moisture and nutrients to the environment, and that doesn't work out too well for the cell. So this is how you answer that back page. But they just put the numbers out there and don't give you any of this information. So now you know. So this is, I won't have like 10 or 15 of these, but I might have a few where I might ask you to determine the surface area to volume, figure out a surface area to volume ratio, and then I might give you a couple of problems like I have here. When we're working with, can I erase this?
Yeah.
yes, ma'am.
When you're working with a bacillus, the easiest thing to do is to treat it like it was a rectangle. Okay? So this would be the height. This would be the width. And this would be the length. So this makes the formula really easy. So how do you figure out the area of a square? It's always height, no, it's volume.
Oh, I'm sorry.
Each end is just height times width, right? But you got 2 ends, right? So it would be 2 times the height times the width. So that gives you both ends, but what else do you have to worry about? You got 4 sides, right? So you gotta have the area of each side. And each side would be height times length. So let's just say let's just keep it even. The height is 1, the width is 1, and let's say the length is 4. So you just plug in the numbers. 2 plus 1 times 1 plus 4 times 1 times 4. So that would be 2, and that would be 16. So you got 18 units squared. So that would be my surface area. Now, Tabitha, how do you do volume?
Length times width times height.
Exactly, length and width and height. So for volume,
It's been about 10
it's
years, I'm
length
sorry.
times width times height. So that would be 1 times 4 times 1 times 1. So that would simply be 4, and that would be units cubic.
Let me write this down.
And other than that, it works exactly the same. So when you're doing your surface area to volume ratio, you just divide both by the smaller number. So it's easy enough, right?
Kind of joke right there, Miss Susan.
Okay, what's the bottom over there?
What's the, we haven't got to that yet.
All right.
We got one other thing to do. So this is actually in your lab book, but I made a copy because I was afraid some of you might not have your lab book with you. So what do we do with all this information when we do a capsular stain, a gram stain, an acid-fast stain, and all these different tests? So how do we use all that information we get? So this is how we use it. So let me go ahead and give this out, and then I'll talk about it.
This is our second episode, right?
Yeah.
This is the one that's gonna make my head explode.
It's gonna be on the Teamsters?
Yeah.
Get some extra.
You gotta keep one.
I got one.
Okay.
Oh.
So,
Well, I just thought I could bring
and you
out
don't have to
a from
memorize
the sheet.
this.
Okay.
You don't have to memorize this.
Lord.
But this is, after you do all of your tests, you set yourself up a data table like this.
Oh.
So you notice across the top, they've got organism, gram stain, morphology, cell arrangement. They did the acid-fast stain, they did a motility test, they did the capsule, they did this endospore stain. And then down the left-hand side, they have all the different species that they worked with. So they looked at each species for each one of those tests. And the pluses or minuses are telling you whether they were positive or negative. They were modal or not modal. Were they acid-fast or not acid-fast? Did they make endospores or did they didn't? Okay?
Oh.
So you would set yourself up a data table like this. Now, I think I made a copy of the other one. Yeah, here we go. So,
Trying to figure out the steps to this thing.
She said the spores are not readily available. Continue incubating the culture for another 24 hours and check it again.
Let's see.
can I erase this off the board?
Yeah, you can. I'm keeping one down for the endospores. You can, but endospores, you drop it.
Okay. So what we do is we set up a flow chart using our data. So they've already started it for you. So if you look up at the top, those are all of the organisms that they were working with. So these are all the organisms that are listed on that other page that I gave you. Okay? So they did the gram stain and divided them into gram positive and gram negative. Everybody see that? Everybody find that? Okay, so let's start on the gram positive side. So Micrococcus luteus, Lactococcus lactis, Staphylococcus epidermidis, Bacillus subtilis, Corynebacterium zoonosis, and Mycobacterium smegmatis. All of those are gram-positive. Then they looked at the morphology. So they looked at which one of those was a rod and which one was a coccus. Everybody see that? So let's just do a little graphic here. So now we're working with gram-positive, and I'm not going to relist all the species, but they did morphology. And then they looked at rods and cocci.
Is this indicating that the gram-positive stains don't come in spiral morphology, or
No.
is it just that
It's
what
just
they
that
have?
species,
Okay, I was
just
just
that
making sure.
species that they were working with. So everybody see the rod on here? So Bacillus subtilis is a rod. Little s, Bacillus subtilis is a rod. Corynebacterium zoonosis is a rod. Mycobacterium smegmatis is a rod. Now what you need to do is look at your list, and you want to find a test that enables you to differentiate this group. So you're looking for a test on here where one of these is positive and the other two are negative, or one of them's negative and the other two are positive. So the easiest thing to do is focus in on the line where Bacillus subtilis is, where Corynebacterium is, where Mycobacterium is. So you look through that column of pluses and minuses, and you're looking for the one that's different.
Spore stain.
The spore
Spore
stain.
stain.
Okay, so if you did an endospore stain, so they can be positive or negative. So who's going to be positive?
Bacillus subtilis.
Bacillus subtilis is positive. Corynebacterium zoonosis and Mycobacterium smegmatis are negative. Now you got to look for another test to differentiate those two. So what would be the other test?
Acid fast.
No,
What did I make?
they're both acid fast negative.
Oh, wait.
So what do you think?
Acid fast and microbiology. Wait a minute. This one, and then
I think this does say that the
acid fast is
stain
hot. It's
the-
showing.
Oh, I'm sorry. I'm sorry. Mycobacterium. I'm sorry. My bad.
You
I'm
okay?
getting tired. So the acid fast stain can be positive or negative. So which one's positive?
Microbacterium.
Mycobacterium smegmatis is positive, and the Corynebacterium is negative. So once you get down to a single species, you're done. So you generate a flow chart to get down to a single species.
What does the biologist end up learning from that?
Would be working with an unknown.
Okay.
Let's say you didn't know what one of the species was. We use a flow chart, just like you're setting up right now, to work our way through all the different tasks to get down to a single organism.
Okay, but so the reason why I ask is because of the endospore stain. Couldn't it just be that the Bacillus subtilis, or how do you say that?
Subtilis.
The Bacillus subtilis. It just so happened to be that particular culture was running out of something. So then that's why it ended up presenting that it was endospore positive. Whereas if you would have seen the Corynebacterium bacteria and it was an older culture, it also would have been an endospore. stain.
Corynebacteria is not an
It doesn't?
endospore former.
Oh, okay.
Ever. So you always have to pick characteristics that they're different and they are persistent.
Okay.
So they're not things that change, so they need to be things that are permanent. So the only acid fast organism we have up here is the Mycobacterium.
Okay.
Makes sense? So let's look at the cocci. So they have Micrococcus luteus, Lactococcus lactis, and Staphylococcus epidermidis. So what test could you use to differentiate those three?
Acid fast. Oh, no,
No,
I'm
not
wrong
acid
again.
fast, not in
Yeah,
this group.
I'm wrong,
That's the group I was
sorry.
looking at earlier.
Capsule.
Capsule, capsule, definitely. So you could do a capsular stain. So it's either got a capsule or it doesn't. So who has a capsule?
The lactococcus
Lactococcus lactis. Micrococcus luteus does not, and Staph epidermidis does not.
Mm.
So now you gotta differentiate those two,
It'll be through cell
okay? So you can look at the cell arrangement.
Oh, yeah. 'Cause
So tetrads identifies Micrococcus luteus, and then irregular clusters identifies Staphylococcus epidermidis. Make sense?
Okay.
So you would have to,
On the test, would we have the chart?
you would have to have the chart.
So you would give us the chart.
You would have to have the
Okay.
chart.
Alright.
And then you simply interpret your results.
Okay.
So you're looking for specific tests that enable you to separate out all the different species.
And if we don't have a test, then we have to solely having to look
You
at the
have
physical.
you have to keep testing.
Uh-oh.
You have to look at the cell shapes. You have to look at the arrangements. You can use any of that stuff to help you differentiate the different species.
I have a question. So, we have to have one left, or can it be like just under each, like a plus or a minus? You know
No,
how you
you
gotta
have to,
one.
you have to have a way to differentiate those two species. So you
Okay.
gotta get down to a single organism in each. Do you guys remember in general biology, you probably did dichotomous keys?
Oh,
When you identified trees and
said
stuff
no.
like
I have a
that?
question.
No?
I have a question.
Oh, my God.
And the reason I brought that up, in a dichotomous key, you've always got an either or. So it takes you down one path or the other path. And you just keep going to those branch points until you get to a single organism. So that's the same thing we do in biology.
So with that one, with the acid fast, the last two you have, you gotta break that down to one more.
No, it's done.
It's done.
See, the only
Okay,
one
that's
that's
what I'm
acid
saying.
fast is mycobacteria.
Okay, cause it's a plus.
This is negative, that's
Oh, okay.
Corynebacterium xerosities. So once you get down to a single species, you're done.
Okay.
Because now you can see and tell the difference.
Yeah, you can
Exactly,
find
you've
the differentiation.
differentiated your
Yeah.
whole group.
Mhm.
If you look at that other side, the gram negatives, so what they looked at first on that side is the cell morphology. So only one of them was a coccus. Everybody see that? Neisseria ceca. So do you need to do anything else there? No, it's already down to one species. If you look at the spirilla, you had Rhodospirillum rubrum. Do you need to do anything else? No, it's already down to one.
Wow,
So
that's-
before Tuesday, you guys try that last one and see if you can differentiate those three.
This the whole
And then we'll
purpose of.
check on Tuesday.
Oh, I'm sorry, I was just like, this is the whole purpose of having cultures, to be able to see different colonies. And this is like, I guess on an even smaller level, to be able to identify what it is you're looking at.
Yeah, when we have an unknown, when you culture an organism from a patient that's making them sick, you don't know
No.
what it is. So you have to go through a whole battery of tests. You have to stain it, you have to look at the cell shape, the cell arrangement. You have to do all these different biochemical tests. And then you can use all that information to help you figure out what it is. You can kind of know what it might be, but you gotta work your way all the way through the chart to determine what it actually is.
That's gonna be what it
Okay?
So we're gonna be working from, from this chart?
You would have to have a chart.
Okay.
You have to have that information.
You'd have to have the information.
Yes.
And then you could develop a flow chart from it.
Okay. But it'll be this chart right here.
It will be a chart.
You don't get that lucky.
But
I'm
it
just
will
grateful you gotta remember
be, it will
on the
be
chart.
just this type of chart. It will
Okay.
have tests
It'll have all
and
the same information.
organisms, all the information will be there, and then you simply have to interpret it.
And we don't have to remember a chart.
No,
like
you don't
that.
have to
Thank
memorize
God, 'cause
this.
I was scared.
You gotta have to remember.
I saw that sheet and I got nervous. I was like, we gonna get
Never
this one.
wise to memorize.
Yes.
Always best to think your way through things.
Yeah,
So any questions about that?
my brain ain't that big.
Who made you in the nursery?
Not for this, so I can't remember. I remember the shapes and what I need, but
Don't
Okay,
move me on something.
so is that good?
you done. You better take a picture. No,
I ain't talking about
just
I'm talking
joking.
about for something else.
I'm just joking.
Okay, can I write?
Oh, you can erase. You can erase away. I'm trying to get the step down for these things because you trying to ask me to do it physically.
You might be
Now,
here doing something
now,
else.
I'm glad you asked that, Darrell. You do not have to memorize the steps to the study. That would be a waste of your time.
I don't
So
know.
are those
You will
gonna be
have a
posted?
protocol. You will have a
Yeah, how we
protocol
do
to
it.
follow. You simply have to do it correctly.
Oh, we're good, Darrell.
Okay, so, I mean, there would be no point in you memorizing the steps.
Okay, so we're not gonna have to know. Next is crystal violet, then,
Now you do know for
Hold
the
on.
gram stain, you need to
Need to
know
know.
those reagents that we used in the gram stain.
Mhm.
The order that they were in and what each purpose each one had, the function of each one.
Well, no other purpose is.
But for the protocol, you
Right.
will have the
when
protocol.
we're about to have to make our own, it's gonna say, get the drop of water, put.
No, I'm not gonna go that far.
But still.
I mean, I
that's what
expect you to know how to do a bacterial smear. I expect you to remember that you gotta air dry that and heat fix it.
Okay,
But what I will give you is, who's got their lab book?
like first the
Yeah.
iodine, then the,
That,
Let's see. Let's get over here too. Oh, here's a well, that's simple stain though. Let's get another one. So if I ask you to do the gram stain,
That's the
you would
last one
have
we did.
this sheet.
mhm.
Okay, so this is the protocol for the gram stain,
okay.
okay? So that's what you would have.
Is the gram stain the last one we did?
Mhm.
Yes.
Is that the one we had two drops of
Yes.
water and then you
All
mix it in the
differential
middle?
stains have at least 2 stains. So the endospore stain is also a differential
So you dry.
stain.
and
That
then
was
you
the one
fix
where
it.
we used the slide.
And I don't know what you do after that.
The negative stain and the Congo red were the ones where we used the other slide.
Oh, you
to
do
spread
crystal
it.
out.
To spread it. That's it. Okay.
Crystal violet
And
first
those were the
for one minute.
I think it was then second.
No, no,
What's it
no,
called?
no,
That's
no.
it.
that was the negative
I know
stain.
that.
That was the negative
Yeah.
stain.
It's gonna
Okay.
be.
So crystal
Negative.
violet.
Oh, wait, I-
Negative
iodine,
encapsulation.
Decolorize.
Alcohol.
And wait.
Oh, yes, sit.
You got it. You got it.
We gonna get this down in bad.
Now, I'm gonna go ahead and introduce you to these last 3. So these are selective and differential medias, okay? I'm gonna set these up and let you guys look at them next Tuesday. It's a little early to set them up today, because they lose their color if you keep them too long. So I'm gonna set them up for you guys, so you'll just have to interpret them and look at them on Tuesday. So all of these are selective and differential.
Notes. I thought I had this chart. Remember? Man, be like, I got all the way to March.
So the first one is mannitol salt agar, MSA for short. Okay, mannitol salt has mannitol in it. It's a carbohydrate. So that's the carbohydrate. Has peptone as an alternative energy source. break down mannitol, so there's gotta be something in there for other stuff to live off of. It's 7.5% salt. That's what makes it selective. Most things won't live at 7.5% salt. So this particular medium is selective for gram-positive microbiology. Selective for gram-positive microbiology. It's the only thing that'll grow on it. And it differentiates between acid producers and non-acid producers.
Gram positive.
The way that it does that is by a pH indicator. So the pH indicator in this one is phenol red. And phenol red turns yellow under acid conditions. And it turns deep pink under basic conditions or alkaline conditions.
You said deep pink under.
Deep, a real deep pink color. So what this tells you is it's fermenting the mannitol. So it ferments the mannitol and produces acid as a byproduct. So that's what creates that yellow color. So this is evidence of fermentation.
So you said the yellow is yellow evidence of fermentation.
Evidence of fermentation. That means there's only one thing in there to ferment, and that's the mannitol. So if it turns yellow, you know it's using the mannitol. If it turns pink, that's peptone utilization.
And you said that it turns pink under alkaline and basic, or basic conditions?
No, basic is alkaline.
Or, I mean,
Basic
okay,
is alkaline, yeah.
cool.
So it turns pink under basic conditions. It's beyond the scope of this class, but you guys remember talking about amino acids? You have an amino group on one end and a carboxyl group on the other end. Remember talking about that? You got a central carbon in here. You got COOH on this side, and you got an NH2 on this side. So that the way that you utilize peptone is by deaminating proteins. So when you deaminate, you cleave that group off. So you end up with NH2, which is reduced to NH3. And NH3 is ammonia, right? It's a very powerful base. So as that base builds up, it makes the phenol red turn pink. Okay? So I'm not going to ask you anything about this, but
Is phenol red or cyclohexane combined with alcohol?
I don't know. I'm not sure.
What's the phenol?
It might be, I'm not sure what the actual compound is. So the way you set this up is, you got a petri dish. Sometimes we just separate the dish into two sides and you streak both sides with a different organism. So let's say you streak this side with Staph aureus. Staph aureus ferments the mannitol and produces acid as a byproduct. So when you come back, you're gonna have a yellow halo around that growth. So the acid is produced, it diffuses out into the medium, and it turns yellow. So you get a yellow halo. On this side, we might put staph epidermidis. Okay, staph epidermidis doesn't use the mannitol, it uses the peptone. So this side will turn deep pink. So when you come back, you just look at the plate. So that's the MSA. The McConkey agar also has lactose in it.
This is differential.
It has crystal violet. And bile salt in it. And those are what make it selective. And this one selects for gram negative. So you remember Staph aureus and Staph epidermidis are both gram positive. So if you streak those on McConkey agar, they won't grow. It's selective for only gram negative.
Can you say that again, Miss?
It selects for gram negative.
What did you say about the crystal violet and the bile salt?
That's what makes it selective. That's what makes it selective is the crystal violet and the gram and the bile salt.
And you said the lactose was
That's the carbohydrate.
carbohydrate. Okay,
So
that's what I was
lactose is
saying.
the carbohydrate.
All right.
Okay. This one differentiates lactose fermenters and non-lactose fermenters. And again, to do that, it uses a pH indicator. So the pH indicator in this one is neutral red. And neutral red turns red under acid conditions. And it remains clear. I think it's 6.8 and up. So acid makes the growth actually turn red. So when you streak an organism on mannitol salt, the colonies will turn red if it's a lactose fermenter. If the colonies are clear or cream colored, whatever natural color they are, that's a non-lactose fermenter. So what makes it work is the neutral red. Whenever you're fermenting carbohydrate, you produce acid as a byproduct. So you're gonna see that over and over and over and over again. So any questions about those two?
What did MSA stand for again?
Mannitol salt agar. Yeah, mannitol salt agar. Last one is EMB. That's eosin methylene blue. So this one also has lactose in it. It's a carbohydrate. This one has methylene blue. And eosin Y. So those make it selective. And it differentiates vigorous fermenters slow fermenters and non-fermenters. Now you notice we don't have a pH indicator in this one. What happens is if the organism can ferment lactose and it ferments it very rapidly, it produces a massive amount of acid very, very early, the acid reacts with the dyes, and that's what gives you the color change. So we actually had an example of this one earlier. I showed it to you. Remember the one with the green metallic sheen? That was this test. So if it's a vigorous fermenter, it uses the lactose very rapidly, produces a massive amount of acid, and you get that deep purple. And you may get that green metallic sheen.
So the vigorous produces the lactose quickly?
It uses the lactose quickly.
Okay.
It ferments the lactose and produces a massive amount of acid
Only
very, very
the
quickly.
vigorous does the deep purple. and
Only the deep purple, and you may get the green. Remember, I think I mentioned the reason that municipalities like Columbus Waterworks use this one is because the most common fecal coliform is E. coli. And E. coli always gives you that green metallic sheen. So that's what they're looking for, is that green metallic sheen. So if it's a vigorous fermenter, you always get the deep purple. But with E. coli, you get that green metallic sheen. Slow fermenters are turned pink. So they're still using the lactose, but they're just using it much more slowly. So you don't get as much acid, so you get a and non-fermenters are just their natural color. So they may be cream colored or whatever, but you don't get any color change if it's a non-fermenter.
And what does EMB stand for?
Eosin methylene blue.
Oh, okay.
Eosin methylene blue. EMB.
Right. Thank you. Okay.
How long does it take for you to see the difference between whether or not, well, I guess it's the color is more so like the indication, like for the vigorous fermenters,
Yeah,
but I didn't know if
color-
you could visually see it on a microscope, like happening as it's like changed.
No, I don't think so.
Okay.
No. Within 24 hours, you usually have the result, yeah. So, any questions?
So you said on the slow fermenters, they use the lactose slowly and they produce moderate amounts of acid, And on the non-fermenters, am I saying that right? Yeah. On the non-fermenters, you said that they're just natural in color, or either they're natural color.
They're gonna be whatever
Natural color they are. Okay.
They're not using a lactose, they're
They're
using
something
something
else,
else in the
okay.
medium. I can't remember off the top of my head what that one has in it, if it's peptone or if it's another protein derivative, but it has something other than carbohydrate that it can use as its energy source.
Okay. Let me write that down.
So, any questions? So like I said, I'll set these up for you, so we'll evaluate the results. Be sure you, finish working your way through this. Be sure you practice your math a little bit if you need to. It's been a while. We won't have a ton of those, but we'll have a few. Don't forget to study your cell graphic. It's a biggie.
Talking about the one you told us to label?
Yeah, the labeling exercise. And don't forget to look at all those examples of the different cell shapes and arrangements so that you can match those up or recognize them when you see them. Okay? Any questions? All right. Well, I think that's it for tonight. Oh my Lord, it's only 7:30. Y'all can find something else to do.
No, we got to study.
I think you got enough to study. I think.
Look, says the one who studies a couple hours before.
I know. Time for it to mind it. That's all I can tell you. Yeah. I gotta go back and get that. I'm gonna spread the
Are we taking a test in here?
What,
Because you said we're gonna have
Thursday?
microscopes.
Yeah, we'll do it down here.
Okay.
On Thursday.
Lord.
Okay, make sure you leave your paper so I can see it. Darrell, you too.
What?
Just leave your paper open so I can see it.
You could be talking to Dre wants to ski and nothing. Like I'm the
Man,
80s.
y'all begging all y'all people here the other day.
I'm the 80s person. Like
I had a long
You
drive.
ain't in no 80s. You go somewhere.
no, I'm saying like that's why I think on the hill. Like I'm like right at the 80 mark. Like, this is a low number. Penny,
Okay.
I'm tired. I see you got a little white out, you know. I see you white out. Hey, what's she over there doing?